Okay, so we've just learned what the definition of the derivative is. Remember the two important ideas we said: it is the limit of the difference quotient. As we see algebraically, it's pretty obvious. And it also is geometrically is the slope of the tangent line, as we're taking the limit of these secant slopes. That will give us the slope of the tangent line. So this is a perfectly good and correct definition of the derivative. It's used in a few different scenarios. There's an alternative definition that's also used in a number of scenarios as well. So we're going to learn a second definition, but it's the exact same idea. We're just making some notational changes to simplify some of the algebra. So if we start with the definition that we just walked through, f prime of a is the limit as x approaches a of f of x minus f of a over x minus a. We're going to do something here. We're going to let x minus a, what we don't really care for is this subtraction inside of the denominator. So what we're going to do is we're going to replace that x minus a with h. So let's see what happens when we do that. So if if h equals x minus a, then that would also mean that we could get x by itself here, and we would see that x is equal to h plus a, or a plus h is how we'll actually end up writing it in the formula. So if that were the case, then we would see that f of x minus f of a, just looking at the difference quotient right now, could be rewritten in the following way. Well, we saw that the denominator of x minus a is equal to h, so we'll just replace it with h. We just also here saw that x is equal to h plus a, so instead of f of x, we can write I'm actually going to write a plus h. Commutative property lets me turn that around, no big deal. So f of a, though, is going to stay the same, and so I have f of a. Now, like I said, there's some value in that. What has happened is we don't have any x's now, and we don't have subtraction or difference in the denominator. So our new limit isn't going to depend on this value x anymore. It's going to be a little bit different here. As we look at this, we see that in the original expression, we were looking at the limit as x goes toward a. So if we were to look at this as x goes toward a, that means x minus a is going towards 0. So as x approaches a, x minus a approaches 0, which means h is approaching 0. So our original definition of the derivative can be rewritten as f prime at a equals the limit as h approaches 0 of f of a plus h minus f of a all over h. So here is our second definition of the derivative. They are just two different ways of saying the exact same thing. We'll see in some scenarios it's a little bit easier to work with one than the other. I don't think one is better than the other, but we'll see multiple scenarios where they each are getting used. So we want to make sure we have both of these available to us. Notice the stars. This is an item that will need to be memorized. You'll see a lot of questions that involve the definition. So you want to make sure you recognize this form. That also would be true of this guy up here. We need to know both forms. So make sure you're working on having that memorized. We will do enough examples that I don't think you'll have any trouble memorizing these. So one other quick comment. We would talk about the derivative at a point. So notice it's a limit, but we're talking about it at a specific point, that point A. And if the derivative exists at that point A, you notice certainly it's possible that this limit might not exist. As we have h going towards 0, that's going to cause issues. So sometimes the derivative doesn't actually exist. But if it does exist, when this limit exists, we say that the function is differentiable. differentiable at that point A. Okay, so there is our second definition of the derivative.